All right, so we are going to look at the derivative of natural log, but before we do that, we need to talk about what a natural log actually is. So, believe it or not, you've been doing natural logs without knowing the definition of a natural log. So, the natural log of x is equal to the area from 1 to t, or 1 to x, I'm sorry, of 1 over t dt, as long as x is greater than 0. So um, this involves that second fundamental theorem where the proof comes from. We're not going to do the proof. I'm just going to show you with Desmos what that means. So the natural log of 2 is actually the area between 1 and 2 of a function like 1 over x. I can use x because now I'm using an actual number there, dx. So if I look from 1 to 2 and I find the area of this integral, that's the same as the natural log of 2. So that's where natural logs came from. And in order to know that, we have to know that, I'm sorry, in order to find the derivative. So right here, if you see, I put 1 over x, because that's what they told me, and I'm looking at the positive, and I'm starting at 1, and my b is equal to 2. So that area is 0.693. So I'm going to find my calculator on my, there we go. If I put in the natural log of 2, so 2 natural log, I get the same number. Notice this number and this number are the same. That's where the natural log came from. That natural log value is an area under a curve. So if I want the natural log of 5, so I made b5. Now the natural log of 5 in your calculator should be 1.609437. Let's try it in my calculator. Again, not very good finding my calculator. I'm going to put in 5 natural log, and I get that same value. So that's what the natural log is. So in order to take a derivative of the natural log, we have to use the function 1 over x. So let's go back for a second. I'm going to go back to basic derivative rules. Do you remember the power rule when we had, like, if I was going to integrate 1 over x squared dx, and I would write that as x to the negative 2 dx. And then the power rule for integration or antiderivative says that I add 1. So that would equal x to the negative 1 divided by the new power. So that's the antiderivative. Notice in all the problems I gave you, I never gave you 1 over x. And the reason is, if you rewrite that, that's x to the negative 1 dx. And if you add 1, you get x to the 0 divided by 0, which we know you can't do. That means this one is special. And that's part of the natural log. So, give me 1 second to answer my phone. Let me hit pause. So with all that, what we're going to talk about today is actually the derivative of the natural log of x. So if you think about it, I was doing the antiderivative of 1 over x, and I get natural log. Therefore, the derivative of the natural log of x is 1 over x. Now, this is the parent function. The derivative of the natural log requires the chain rule. So we're going back to derivatives. We're going to do derivatives, integrate for this last unit. So example here, if I want, this is the basic definition. So if I want the derivative of the natural log of 2x, that would be 1 over 2x, because this is going to be my inside function, even if you want to put parentheses around that. But then I'm going to have to multiply by the derivative of that because it's not just x anymore. So I have to use the chain rule a lot with these. So what is the derivative of 2x? That's 2. And then you do some fun old algebra, do a little cross canceling. You just get 1 over x. Now, I could have done this a different way. I'm not going to get into that right now. I could get 1 over x by rewriting this as just the natural log of 2 plus the natural log of x, and then doing the derivative, but I'll show you one like that in a second. So let's try another one. The derivative of, let's do the natural log of x squared plus 1. So the rule says I'm going to put 1 over x. Well, this is now my x. So it's 1 over x squared plus 1. But it's not x, and I need the derivative in terms of x, so it's chain rule. Remember, this is the inside function. So then I'm going to multiply this by the derivative of x squared plus 1, which is 2x. There's no canceling on this one, so it's just going to be 2x over x squared plus 1. All right. Let's add a new rule, or not a new rule, let's combine two rules. So let's say we want the derivative with respect to x of the function x times the natural log of x. So this one's going to be a product rule because I have x and I have natural log of x. So I'm going to use the product rule. So I start with the derivative of the first function, which would be 1, times the second function, which would be the natural log of x, plus I keep the first function, which is x, times the derivative of that second function. The derivative of natural log of x is 1 over x. Then I simplify. It looks like these could cancel. So I get the natural log of x plus 1. That is my derivative. Let's try another one. How about the derivative with respect to x of, how about we do the natural log of x. Let's cube that whole thing. Let's write it like that. So I got to think about that for a second. That looks like a chain rule because we have an outside power and we have an inside. So some of these might even require two chain rules. Well, this one I think is just one. So we're going to do this power first because it's on the whole outside. So this becomes 3 times the natural log of x to the second power. So that's the first part, and then we have to multiply by the derivative of the inside, the baby. So what's the derivative of natural log of x? That would be 1 over x. And you could leave it like that. I would probably rewrite it as 3 times the natural log of x, that quantity squared, over x. You can leave it however you like on that one. Okay, let's try another one. Let's try one with, I can show you that I can make it easier. Let's say we have f of x equals the natural log of the square root of, let's x plus 1. So this one looks like it'd be complicated because it has that square root in there. But what you could do is, remember the other day we talked about expanding and condensing? Well, I know that this square root is a 1/2 power. So I can rewrite this as 1/2 the natural log of x plus 1. So I still haven't taken the derivative, I'm just going to rewrite it. So now if I want the derivative of that, the 1/2 is a coefficient, so it can stay. And then I need the derivative of the natural log of x plus 1. So that's 1 over x plus 1. And then I'll need to multiply by the derivative of the inside, the baby inside, which would just be 1. So you could write that lots of different ways. I'd probably just do this, and that would be your derivative. Let's try one that's a little bit more complicated so you can see how, if you have, let's say you have the natural log of the square root of x plus 1 all over 2x plus 3. So if I was going to do this without using logarithm properties, I would have to use the quotient rule and the chain rule and some power rule stuff. But if I use my log properties and I expand this, I can make it easier. So I'm going to rewrite this. So first of all, remember this square root is the same as that 1/2 power. So it's going to be 1/2 the natural log of x plus 1. And then remember dividing is a subtraction. So minus the natural log of 2x plus 3. Now I'm going to go ahead and take the derivative. So the derivative of this 1/2, again, is a coefficient. The derivative of natural log of x plus 1 would be 1 over x plus 1 times the derivative of that inside, so just times 1, minus, this is going to be 1 over 2x plus 3 times the derivative of the bottom or the inside, so that'd be times 2. So you could rewrite this as 1 over 2 times x plus 1 minus 2 over 2x plus 3. I I'd probably leave it like that. I mean, if you were solving for something, you definitely could like butterfly that if you wanted. Like if you're trying to find a critical point or something like that, but you don't have to. Let's try one more. We're going to go back a little bit to something we did. We're going to look for the equation of a tangent line. So that's what I'm going to look for. Let's say I have this, y equals the natural log of x to the fourth. And I want to know the equation of that tangent line at 1, 0. Again, there's a couple ways you could do this. The derivative of this with respect to x would be 1 over x to the fourth times. The derivative of x to the fourth would be 4x cubed. And then you can simplify that. That's just going to equal 4 over x. So that's my derivative. Some of you are probably thinking, could I move this 4 out front first? Absolutely, you get the same answer. So then this might be a refresher that we need. How do we find the equation of the tangent line? Well, first we need the slope. So to get the slope, we have to put x into your derivative. So my slope, m, would be 4 over 1, which is just 4. The equation of the line then would be y equals 4x plus b. How do you find b? Well, you're going to plug in 0, and you're going to plug in 1. So 0 equals 4 plus b, so b is negative 4. I love it when I do that and I can't find it. Hold on. So b is negative 4. So y equals 4x minus 4. And just to show you what that looks like visually real quick, here is the natural log of x to the fourth. And we're looking at the point 1, 0, which is right there. So the equation of the tangent line, y equals 4x minus 4, is right there. And that's what we did. So those are derivatives of natural log. Do your assignment. Make sure you email me if you have questions. I still have not been receiving tons of questions, so I'm assuming you know what you're doing.